So, hi and welcome everyone to lecture 21 or lecture 5, just depending on the count. So today we're going to treat the accelerated gradient descent. So I think, at least my impression, it's one of the greatest achievements of the last century when it comes to convex optimization. And maybe also splitting methods fit the bill, but this acceleration technique, it's amazing. Okay, so I think we have a little bit too much stuff for the lecture today, but I couldn't split it otherwise. So we would like to prove two things for two different gradient schemes, prove convergent and how fast they converge, at least in the descent of the function value. One for convex and L-smooth functions, and the other for strongly convex and L-smooth functions. The schemes are slightly different, and we'll see that they are the proofs are very different. Okay, and let's see. I think in the end, so the proof of the second result, the linear convergence of the accelerated scheme for the strongly convex case and smooth case, I think I have to skip a few details. They are mainly just technical calculations, so one can just do them by yourself, but it just takes some time. Okay, let's get started. So our lecture is lecture 21. Accelerated gradient descent. Actually, they're often called accelerated gradient descent, but as we will see, you will see what the fact is that they are not really descent methods anymore. So, and let me first give you the scheme to show you that it's really, really simple. So the accelerated gradient schemes all go like this. You start with an x0, but also with an x minus 1, so kind of two initializations in your ambient space, and then you just iterate, and so you take and of course you start with k equals 0 and iterate, you define from x, and then the first thing you do is you do an auxiliary step. So at xk, you go to some yk, and this looks like this. This is alpha k times xk minus 1. And then the step goes, then xk plus 1 is doing a gradient step from this y point on, and by some step size. So this here should be an xk plus 1. So that's the scheme, that's all. Initialize with two values, arbitrary, doesn't matter. And then do these two steps. So first from xk and from the xk and the previous one, do this step to arrive at some yk, and from that yk you do a gradient step. So let me just depict what this is doing. So assume that here is your xk, and here has been your xk minus 1. Xk minus 1, so the previous one. So what does this step do? So where do we find yk? So this alpha k is usually taken as a positive number. As you'll see, it's often between 0 and 1. So what this is, this is xk plus a vector, and this vector is this one here, which is the one which points from here to there. So xk minus 1 points from here to there. So what we do is we take this direction here and go a little bit further into this direction. So here we see the yk. So it's an extrapolation. So we move in the direction where we came from a little bit further in this direction. And from that here, say we just move into the direction of the negative gradient and end up here somewhere with our xk plus 1. Depending on where the gradient points to. But this step here pushes you a little bit further in the direction where you wanted to go anyway. Which sounds a bit strange, but this is how the method works. And so the two parameters involved here, this here, I don't know if it has a common name, I call this extrapolation parameter, extrapolation, because it kind of, it extrapolates where you came from. And again, this here, this h is as before a step size. Okay, so what, and surprisingly, if you choose these things well, this method does converge. Okay, and I can't give you an intuitive explanation why it does, but I can prove that it does so. One thing which is true is that this method is not a descent method anymore, although it's often called accelerated gradient descent. So what does it mean? It means that the values f of xk, they do not decrease in every step. They may go increase and they may oscillate somehow, but they will go down in the end. And so to prove convergence for these accelerated schemes, we need a technical lemma, which looks, to me, it looks totally strange, and I really don't know why it exists and what it does say, but we'll see that it is really, really helpful. So the lemma goes as follows, and it's a simple observation. It goes like this. So if f is convex L smooth, the step size is positive, but now it's bounded by 1 over L, not 2 over L, as we had before a few times. And then we just consider one step of gradient descent from x on. So, sorry, 1 over, no, h is okay, h times gradient of f of x. So this x plus is just the gradient step of a from x. Then it holds for every y. It holds that if you consider f of x plus, so the result of the gradient step, plus the square distance from x plus to y divided by 2h, that's still smaller than f of y plus x minus y to norm squared 2 over h. So that's the lemma. And I find it pretty confusing because the variables appear in in places where I did not expect them to. So, and there's no typo in here. So this is f of x plus, that's f plus, and that's y. And here's y, and there's x, and there's y. Yeah, so this is just how it is. And the important thing is that's really, no matter what y is, right? You have this x plus and x, they are connected via a gradient step. So you make from x, you make a gradient step with a step size which would guarantee a decrease. But here you get decrease of something totally different, and especially, and also it really doesn't, not all of these really fits together. But we'll see that this inequality will be the one which really makes the proof work. And to prove this lemma, it's not so difficult. Yeah, let's do it. Maybe I just start calculating. So we start from the left-hand side. And in the first step, we just plug in that that x plus is this here, right? So we just use this definition here. Oops. Add the point here in the square, and then we expand the square. So we just keep our f of x star, x plus, and we plug in x plus is this and expand the square, and then we get x minus y. We keep these two things together. We have a minus, so we have a minus here, gradient f of x minus y plus h over 2 here, because of the h cancels here, but here we get h over 2 norm of the gradient of f of x squared. So it's not estimated, we just expanded the square over here. So now we use that this is also a gradient step over here. We know that if we do a gradient step, then we have decreased the function value. So this value here is smaller than f of x plus something, and this is exactly yeah, so what do you need here? Probably I show it down here. What we need is that f of x plus is smaller than f of x minus h times 1 minus LH over 2 norm gradient squared. That holds for all gradient steps, so we proved and used this before. And here we have that h is smaller than 1 over L, so this here is smaller than 1, and actually we could also estimate from above by, smaller than 1 over 2 actually, it's estimated from above by f of x minus h over 2 norm gradient of f of x squared. So this here we use this inequality here. So this here also goes in there. Okay, and now we use this for the f of x plus, this outer inequality, and see that this gradient term here actually cancels. So we estimate we make this larger by putting in this, then the gradient term cancels, and we are left with f of x plus this gradient of f of x, x minus y, yeah, like this, probably plus, oh, and this has sorry. If I put a plus here, I have to swap the order here. So this is y minus x in there, and we still have this x minus y squared 2h. Okay, and yeah, finally, yeah, we just used use convexity once. Actually, we did not really use convexity. We only used smoothness over here. Now we use that f is convex to estimate this guy from above by f of y. F of y plus x minus y squared over 2. And that's already it. So and all the ingredients has been used. So the gradient step has been used once here, just for expanding the square, and once here to estimate f plus by f of x, and then for this we use the L smoothness, and then here we use convexity again to convert these two things to f of y. Okay, so that's it. That's the lemma, and now we're going to see how we use it. And before we do that, we make one slight change in notation. So we change notation and write the extrapolation step yk as xk plus a little bit weird quantity, but we'll see that this will play the most important role. And will be, so we rewrite this alpha k by tk minus 1 divided by tk plus 1. So this here was our alpha k, and this was the extrapolation. And we just write it differently. We just write we express it by the sequence alpha k of extrapolation parameters by some other sequence tk minus 1 and tk plus 1. So it's just a change of notation, and we'll probably see a little bit more details about this change in notation in the next lecture. Okay, so we do that and express the extrapolation step like this, and not with the alpha but with this. So, and then here comes the proposition which already proves everything which we would like to know about the accelerated gradient descent. Proposition 21.2. So f convex L smooth, f star is minimum, so it has to exist, to arbitrary initial values. The step size, of course positive, but bounded from above by 1 over L, and tk such that, so this tk which comes from here has to fulfill two things, no, three things. We have to initialize with 1. They have to stay larger than 1, and we need the crucial inequality, which is strange at first sight, but we'll see. Tk squared minus tk plus 1 squared plus tk plus 1. This has to be non-negative. Then it holds for xk generated by this here. This is 2 stars, and the gradient step here gets 1 star. So by the generated by these two things, extrapolation and gradient step fulfills that the function value at the kth iterate minus the smallest one is bounded from above by the initial distance to the minimizer, and then here comes 2 times the step size times tk squared. That's the proper position. So we have an upper bound for the distance to optimum, which depends on the step size, on the initialization, this is a square here, but also on the tks. Okay, and we'll see that this is the magic which happened here, that we can choose the tks such that they grow pretty fast enough that this here will be small. And we'll see the faster we can make the tks grow, the better this result will be. And we'll talk about this after we've proven this estimate here. Okay, so let's prove it. And the proof starts pretty strange by a very, very clever thing, which I can't explain where that comes from, but it works. So we use lemma, of course, we use lemma 21.1 with the following things. As x, we use the yk, then of course the x plus has to be the xk plus 1, because xk plus 1 is a gradient step from yk. But as the y in the lemma, we use something a bit strange, which is 1 minus 1 over tk plus 1 times xk plus 1 over tk plus 1 times x star. Okay, let's just do it. So this makes sense because this is a gradient step from there, and this is just an auxiliary point which we can use, and we take a convex combination between the iterate, the previous one, and the solution. So if we do that, do you want to have a look at the lemma again? So we just here we use over this x plus will be xk plus 1, this x will be yk, and this y, which appears 3 times, will be this complicated expression here. Okay, so this gives us f of xk plus 1 plus this term here is then xk plus 1 minus this guy over here, right? 1 minus 1 over tk plus 1 xk, and again minus 1 over tk plus 1 x star squared divided by 2h, and smaller equal f of, again, this guy here, 1 minus 1 over tk plus 1 xk minus 1 over tk plus 1 x star plus, and then here we have the difference of x minus yk, x is x minus y, x is yk, minus this guy again here, 1 minus 1 over tk plus 1 xk, 1 over tk plus 1 x star squared over 2h. Okay, that doesn't look very nice actually, but you will see that it's good. So we're gonna continue here, but now we make a few auxiliary calculations. First, we define initial variable which makes just Link's life easier. X uk plus 1 will be defined as xk plus, and now it's just tk plus 1, xk plus 1 minus xk. So it's something which is in between xk and xk plus 1. And if we do that, we can express this expression over here is xk plus 1 minus 1 over tk plus 1 xk minus 1 over tk plus 1 x star as, and yeah, if you do that, it's just 1 over tk plus 1, and then you can divide it as uk plus 1 minus x star. So that's the first thing, and so this happens towards in here, and this here also gets simpler if you use this uk. So the same thing here with yk minus 1 over tk plus 1 xk minus 1 over tk plus 1 x star. This is then equal, oh sorry, I'm off screen, so once again, so I wrote down the thing which is here in the right hand, in the square on the right hand side, and then yeah, plugging in the yk, and doing some manipulations. So remembering that the yk is actually here, this is the same as where we have it over here, that is x, oops, k plus tk minus 1 over tk plus 1 xk minus xk minus 1. Put this in here, do some algebra and clean up, and you will see that in the end this is exactly 1 over tk plus 1. Again, here only uk minus x star. So, oops, this is just some calculation. It's not totally not so hard, but yeah, just not so obvious in the first place. But if you know that you should get there, then that's fine. It's not that hard. Okay, so this we have that, and we're gonna use this to clean up my desktop here. So we plug this in there, and this in there, and also in there. No, there we don't do anything. No, we keep it here. Yeah. Okay, so using this, so we get on the left hand side we still have f of x k plus 1 plus, and this has been simplified here in the square. We have now this here, so we get 1 over tk plus 1 squared out. So we get here uk plus 1 minus x star squared over 2htk plus 1 squared. So on the right hand side we have, so it's this here, and here we just use convexity of f, because that's the convex combination of xk and x star. So it's smaller or equal than 1 minus 1 over tk plus 1 at times f of xk. Actually there is a typo in here, because this has been a plus all the way. Sorry, this has been a plus, and here you also have a plus 1 over tk plus 1 f of x star. And but the square here, which looks complicated over there, it's also simple because we have just this here. It's also so then of the form uk minus x star squared divided by 2h, and still tk plus 1 squared. One really has to keep track of the indices here. This is a k plus 1, this is also a k plus 1 actually. Although that's a k plus 1 and that's a k, so they are not the same. Okay, so why is this good? It's not immediately clear yet, but we can just rearrange it. So bringing the norms on the one side and the f to the other side. And I guess I think it's just like this. Yeah, so and what do we get? So we can write this as f of xk plus 1. And here I would like to subtract an f of x star. So this hasn't been before, I just subtracted it, so I have to add it back again. And to add it back again, we can do it like this. So we bring this to the left hand side, we get a minus 1 over 1 plus tk plus 1 times f of xk. And since I subtracted here an additional f of x star, and we also have this, we can write it like that. So now all the f terms on the left hand side, and on the right hand side I just have the difference of these two norms. So this has the positive sign, uk minus x star squared over 2htk plus 1 squared minus uk plus 1 minus x star squared over 2htk plus 1 squared. Okay, so now so we would like to write a little less, and so we make some abbreviations. These guys here will be called f k plus 1. So this here is then fk, and this guy here will be called I think just vk. So this here is vk plus 1, and with this I just mean the norm squared, not the full fractions here, only the norms squared. So if we do that, we multiply by tk plus 1 squared. And using these abbreviations, what do we get? If you multiply by tk plus 1 squared, we get here tk plus 1 squared times fk plus 1 minus, and here we have to be a little bit careful. What do we get here? We get, of course, a tk plus 1 squared minus a tk times fk. And on the right hand side, this is then just vk minus vk plus 1 over 2h. So this is my f and this is my t. I hope you can distinguish the f's and the t's. So the t's have something like this and the f's do something like that. So, and now that's the magic equality, because if we now take this inequality and sum it up with the previous ones, so we sum these equalities up, we have on the right hand side the telescoping sum, and here something accumulates, but we will see that this is good. So sum up. From 0 to capital K plus 1, something like that. So that we end up with the last here is t capital K plus 1 squared, f capital K plus 1. And here, the terms do not really cancel, but we just put them under a large sum. And the large sum goes then from K from 0 to capital K. And here we get, if we look carefully, it's tk squared minus tk plus 1 squared plus tk plus 1 times fk. So this is if we sum up the left hand side for k from 0 to k plus 1. So this is the last one, and all the others we put together like that. And I think did I miss something? No. Okay, on the right hand side it's simpler. On the right hand side, all the sum, everything cancels with the previous one except for the first one, which stays here, and the last one, which is that. Okay, so and why is this good? Basically we're done now, because by assumption these guys here are non-negative, and this is non-negative anyway because it's the distance to optimality. This is also non-negative. So we can just throw this full sum away and are left with, so this is 4. So because this here is both non-negative, we get fk plus 1 smaller equal, and we also, I guess, we throw also this vk plus 1 away because this is supposed to go to 0 anyway, but we don't care too much. It's smaller than v 0 divided by 2htk plus 1 squared, and this, just write it out, that's f of x k plus 1, I'll have a look in a second, minus f star smaller equal to, and this v0 is actually u0 minus x star squared divided by 2ht capital K plus 1 squared. So where's this question? T K plus 1 squared and fk. Is it from here? Probably. So in this so here I just rearranged, so in the sum, so where does that come? Okay, so probably we should, so to see where this comes from here, so this not, I did not add something or anything could go from here from there. I just, what you can do is you write down this for k equals 0, for k equals 1, k equals 2, and so on, and you sum all these inequalities up. And then here, this comes from the two summands, one from the one inequality, one from the next inequality. So, and I guess this is the one coming from, which comes from where? Let me check. Maybe I should write it down. I try to write it down. So if we have this for 1k and for the previous case, so for 1k we have tk plus 1 squared fk plus 1 minus tk plus 1, oh, tk plus 1 squared minus tk fk, and then the previous one has been tk squared fk minus, and then we have tk squared minus tk minus 1 fk minus 1. And what we do is we collect these guys together here. So if you first, we subtract these guys together, and then we get exactly this tk plus 1 squared plus, minus minus gives plus. So no, this, where did it come from? So this is tk squared fk, tk plus 1 fk, and this should be tk. Should it be tk? Is this a typo in the lecture notes? No. Maybe you got the signs wrong. Sheesh. tk plus 1, tk. So I hope everything is correct over here. Oh yeah, this is tk plus 1, right? You are right. That's also k plus, oh yeah, good, thanks. Good. So good that you take care. This is the k plus 1 actually, and then we get a k plus 1 actually here, and then everything makes sense, right? Then this gives 2, yeah, then everything makes sense. Okay, sure, good. That was a typo, good that you catch that, okay. And then we arrive here. Great, thanks. Good. Okay, so actually also the proof is done. The only thing which we have to observe is, that u0 is also x0. And I think this comes just from the definition which has been, I don't know, somewhere in the past. UK. Yeah, so this just comes from the definition. If u0, then we have here k is minus 1, and you have t0, which was supposed to be 1, so this u0 is actually x0, and then we are done with the proof. Okay, good. Okay, so and now how do we get something out of this? So now how do we choose our things? So one thing is clear: the step size h. The larger the better, right? The larger the h, the smaller the right hand side. But we have an upper bound here which we needed in the derivation, so h, setting h to 1 over L is the best we can do when it comes to the upper bound. So what do we do about the tk? We want the tk to grow, but we need to respect this inequality here. So need tk squared minus tk plus 1 squared plus tk plus 1 larger equal 0. And we also see that the proof is more efficient if this is always fulfilled with equality, because then we don't throw away anything in the estimate. And that's what we're going to do. So just so one way to choose it is assume equality. If we assume equality, we got a quadratic equation for tk plus 1, which we can solve, and we will get tk plus 1 is equal to square root of tk squared plus 1 over 4 minus 1 over 2. Plus 1 over 2, sorry. That's so if you take inequality here and solve for tk plus 1, that's the root you would like to get, because you would like to have this tk growing. So of course there is another root, but this is the better one. So and this you can use. So you can just use this tk's for your method, and of course and h equal 1 over L is best when it comes to upper bound on the right hand side. So if you would like to have it a little bit simpler, you could also say tk plus 1 to make it a little smaller. So this also works. So this works. The tk will grow, so that's immediate. But you could also omit this 1 over 4 here. then the next tk plus 1 will be a little smaller, and if you omit it, you would get tk plus 1/2. Right? If this goes away, this is just tk because they are non-negative. You will just add 1/2 in each step. So these two things would work. So this and this both work, and they both grow. And you see this grows linearly. For each k, you add 1/2. So this goes like k. But if this goes like k, this upper bound here drops like 1/k squared. And that's the nice thing here. So this t, we can make this t grow like k. And actually this here grows a little faster, but if you do the math correctly, it grows just a very little faster. It really is not worth the effort to do that. Okay, we collect these things in another result, and I'll probably skip the proof and do it in the next lecture because we have some space over there. So one corollary which you can do, it's 21(3). You can take the alpha k, so you can just revert to the alpha k, and this then looks like k plus 1, k minus 1 over k plus a, for some a larger equal to 2, and h may still be like this, and then you get f of xk minus the best value smaller equal to, you get a squared x0 minus x star squared over, and here you get 2h k plus a minus 1 squared. Okay, so I don't prove this. You can look at the lecture notes, but I also will say a few things next. So you need, oops, there's a typo here. Okay, what you see here, this upper bound is better the larger the h, we talked about that, and also the smaller the a. So best for the upper bound is h equal to 1 over L, and a the smallest possible, which is 2. And then this specializes to the upper bound. This is 2, this is 2 squared is 4, divided by 2 gives 2. Let me check that I arrive at the right thing, right? Then you get 2L x0 minus x star squared divided by, this will be k plus 1 squared. So that's what we get as an upper bound for the decay, and it really decays like 1 over k squared. So, and recall that, so maybe I should write down everything. So actually there's no fk here, this is just f of xk minus f star. And the lower bound we got from our worst case analysis was, I recall it from here, so it was 3L x0 minus x star squared divided by, and then we had 32 k plus 1 squared. And we see we're not so far off, so we're still by a constant. So here we have the expressions are totally the same except for the number. Here the number is 2, and here the number is 3 over 32. So this is 1/10, this is 2, this is kind of 20 times better, but nothing more. So it still goes down like k plus 1 squared. So we've come pretty close. And actually I don't know the current state of the art. I think one can get this a little lower still. I don't know the best lower bound which is available right now, and I don't know how close these two things are together right now. So but that's already pretty nice. Okay, so that was the accelerated gradient method for the simpler case. So actually the proof was fairly short. So a few calculations with a few indices. So but now the proof for the accelerated method for the mused only convex case, this is a different beast. So, but okay, I go through it, and probably we just have a look at the PDF at some point, because it's really tedious to go through all the calculations. But let us try. Okay. So here that was that, and now we go to mu strongly convex and L smooth. Okay. So let's write down the theorem 21.4, which then already gives everything we need. So f should fulfill this. Mu, sorry. So theorem 21.4, f should be mu strongly convex and L smooth, which means our condition number q is then L over mu. We're going to use q actually in our formulations. Again, f star is attained, the minimum. Okay. And now we initialize, do it slightly different actually, but it's basically the same. We can also initialize with x0 and y0, arbitrary. And now the iterates go like this. So I just write it in a different order. So we first do the gradient step, xk plus 1, which is the one from yk. And I just write it already down with 1 over L, gradient f of yk. And now the extrapolation gives yk plus 1 is equal to xk plus 1. And now comes a fixed extrapolation step. And this is by square root of q minus 1 divided by square root of q plus 1. So that's the iteration. It's basically the same as before. This here is our sorry, this was the step size, so this was blue. So this is the blue step size h or hk, and this here is the green extrapolation alpha k. And they are both fixed, right? They are both do not depend on k. So you can use the fixed extrapolation parameter. It looks simpler, but the analysis is kind of more difficult. So what do we have then? What's the conclusion? The conclusion is then we have first that the difference in value is bounded by 1 minus 1 over square root of q to the k times mu plus L over 2 x0 minus x star squared. And here we have for the norm difference squared, smaller equal than, and this is just 1 minus 1 over square root of q to the k over 2, unfortunately. And then we have another factor, square root of q plus 1, and here we have the initial distance. So and that's a little far off from the optimal. So I want to compare these upper bounds here to the worst case lower bounds we know, and we'll see the difference is also not totally small. So, but this is much faster than for the gradient method. Can compare this. So, okay. So we still have 45 minutes, and maybe we make this short break right now, and then I try to go through the proof somehow, even though it's a lot of technical calculation. So first we're going to relax for 2 minutes, and I'll be back in 2 minutes. So see you then. Okay, let's go. So I think the proof has about 4 steps, 5 steps, and one has 3 more sub-steps. So let's go. So what we do first is, so we define a lot of quantities which at first seem unrelated to convergence, but they will be in the end. So the first quantity we do is we define auxiliary functions phi 0, a sequence of functions, and we start with this f of y0 plus mu over 2 x minus y0 squared. So it actually is a square function, right? This is just an offset plus a square. So it's a strongly convex function. And recursively we define phi k plus 1 of x as, and this is now a bit strange, 1 minus 1 over square root of q times phi k of x plus 1 over square root of qf also times f of yk plus gradient f of yk x minus yk plus u over 2 again x minus yk squared. So okay, so we defined it, and this is, I think, so this is all due to Nesterov and this book, Lectures on Convex Optimization, or Introductory Lectures to the Convex Optimization. And he calls this thing an estimation sequence because we will see that this somehow governs the convergence of the function values. So because f is mu strongly convex, we can get that this phi k plus 1 of x is bounded from above. So I think this guy here just gives you an f of x, right? So we have this smaller than 1 over 1 minus 1 over square root of q times phi k of x plus 1 over square root of q f of x. Okay, that's the first step. Okay, second step, so we claim that we can get a recursion which looks like this, that this phi k of x is below f of x plus 1 minus 1 over square root of q to the k times phi 0 of x minus f of x. So we claim that, and it's true. So what? First, let's check the case k equals 0. Yep. Yeah. So k equals 0. And this gets 1. Yeah. For k equals 0, it's trivially true because it's this will just the factor will be 1. And f cancels, and this is just phi 0 smaller than phi 0. So k equals 0, it's just finished. And then for k, we proceed by induction. So we assume that the case, the inequality is true for some k, and then we check it for the next one. So we just write down so we just use this inequality here, which you have already seen. So it's 1 minus 1 over square root of q phi k of x plus 1 over square root of q f of x. And then we use this inequality here. Yeah, then it gets longer a little bit. 1 minus 1 over square root of q times the full thing over here, f of x plus 1 minus 1 over square root of q to the k, phi 0 of x minus f of x, and we still have this plus 1 over square root of q f of x. Yeah, and if you clean everything up in here, you see that you get here another factor to the k minus 1, and this guy, these minus and plus cancel. And you get this f of x. So it's actually it's f of x, which comes from here, and then here this you get one minus k plus 1. Okay, so that was just a simple induction. Okay, so next thing is we claim that the function value at the kth iterate is actually smaller than what the phi can be smallest possible. Okay, so that's good here if you have a look at this. So this would then be an upper bound for f of xk plus 1 actually, no matter what x I put in there. And so here we have something where you already have a factor like this, which looks nice, and so it seems to go in the right direction. Okay, so the case k equals 0 is again because for k equals 0, this phi, yeah. Yeah, so for k equals 0, we have this here, which is minimal at x is equal to y0 and y0 is x0, and that's fine. Okay, so the k equals 0 case is done. And again we proceed by induction, but first we denote the minimum value here of the phi k by phi k star. Okay, and then we get so f of xk plus 1 is smaller or equal than gradient step from y minus 1 over 2l gradient f of yk. So, and now yeah, we just throw in things and cancel them again, so we can just we add and subtract a few things to write this as 1 minus 1 over square root of q times f of xk. So we added this full term here, but we subtracted basically once again 1 minus 1 over square root of q times f of yk minus f of xk. And so here we again added or subtracted this 1 over square root of q of f of yk, which we add back again. And we still have to subtract this 1 over 2l gradient f of yk squared. Okay, and here we see this guy here, f of xk. This is by induction smaller than phi k star. Oh no, by definition. No, that's our claim. It's by induction. Sorry, this was by induction. And this here, by convexity, we can bound this from above by gradient f of yk minus yk minus xk. So, and if we plug this all in, what we need to show is the following. Oops, is this a typo? No, it's not. We need to show that this phi k plus 1 star is then still larger than 1 minus 1 over square root of q times phi k star plus 1 minus 1 over square root of q times this gradient f of yk minus xk plus 1 over square root of q f of yk minus 1 over 2l gradient f of yk. Okay, so this is what we need to show now, and this will gonna be also not so simple. Okay. Oops. Okay. Oh wow, that's a bit missing. Okay. So, so we would like to show this here, and so if you now have completely forgotten why and where this came from, you're on the same page as me. So it's it is confusing, but so each single step is not so hard. So we need to show this. So there are sub-steps to do this. So substep number A. So that's what we'd like to show. And substep number A is an observation which we could have done early on, namely that these phi's, they are all quadratic functions. They look pretty complicated, but you'll see that this phi 0 has a Hessian which is just mu times the identity. It's just mu because the x only appears here. So, but then recursively, so this Hessian here is mu times identity, and this is linear, so the Hessian just vanish, and this is the only other term where x appears. So this here is mu times identity. This here, the Hessian is mu times identity. The 1 over q is square root of q cancels with this, and so recursively you get that this for all k is again mu times identity. So the phi k, which don't look like this in the first place, they are all just functions of with this Hessian. So as a consequence, we know that the phi k of x can be written as the minimum value plus a square at some point, and in front of the square we need to have mu over 2 x minus something. So this function has its minimum at phi k star. Phi k star is the minimum by definition, and we know the Hessian has to be mu times identity, so it has to be, it should be able, and we have to be able to revise it like this for some vk which we don't know yet. So, but on the other hand, one can get a recursion, so by just taking the derivative of phi k and setting it to 0. So, so the yk is now the place where the minimum is assumed. So we know that phi k of vk is equal to phi k star, or put differently, the gradient of phi k at vk has to be 0 because this is the minimizer. And if you plug that, or if you have a look at this here, taking the derivative, setting it to 0, you get a recursion for vk. So vk plus 1, you can see that this will be 1 minus 1 over square root of q times vk plus 1 over square root of q times yk minus, and here a little rearranging gives you 1 over mu times square root of q gradient f of yk. Yeah. So in the, oops, oh sorry, I've been off screen the full time. So what we do is we use the recursion for phi, taking the gradient of the full recursion for phi, and turning this into a recursion for the vk's. It's in the side remark in the lecture notes, and you'll end up with this here. Vk plus 1 is equal to 1 minus 1 over square root of q vk plus 1 over square root of q yk minus 1 over mu times square root of q gradient f of yk. So that's the recursion for the v's. Okay, so now now it gets even worse. I don't know. So it's a page of calculations right now. So I face a page of calculations. It's still in step B, which is the longest one here. So what you then can see that this phi k plus 1 star plus mu over 2. So this is how it looks like here. Yk minus vk plus 1 squared is then equal to phi k plus 1 at yk. Yeah, let's just plug that in, and now we use the recursion for the phi k plus 1, and we can write this as 1 minus 1 over square root of q, and here this phi can be written as phi k star plus mu over 2 yk minus vk squared, and the recursion also has a plus 1 over square root of q f of y k. Okay, we could just pour that out. Yeah, we could also just, I think I just omit this. So the recursion for the v's will show you that this guy here, and this gets now a little longer, actually looks like, and I'll just write that out once probably, so we just put the recursion for v in here. Oh, and no, sorry, that was wrong. We put it in here. We put the recursion for v into here, yk minus vk plus 1, plug this horrible term in there, and just expand the square, and we get 1 minus 1 over square root of q squared times yk minus vk squared plus 1 over mu squared times q times the gradient of f at yk squared minus, and the inner product has a larger coefficient, it's 2 over mu times square root of q times 1 minus 1 over square root of q times the inner product of gradient of f at yk minus vk minus yk. So yeah, now we have this horrible expression, and now we clean everything up. Actually, I'm already on page 9, I guess, right? So we clean everything up, and it's not that simple yet. We still get something which is a little longer. I probably skip one of the cleanup steps. We get that phi k plus 1 star is actually equal to, and it's still a long expression, 1 minus 1 over square root of q times phi k star plus 1 over square root of q f of y k plus mu over 2 square root of q times 1 minus 1 over square root of q times yk minus vk squared minus 1 over 2l gradient f of yk squared, and still plus, and we get 1 over square root of q times 1 minus 1 over square root of q gradient f of yk vk minus yk. Okay. Okay, that's not totally nice yet, but we can make it a little simpler, not so much, but in the end, so we are almost where we wanted to be. Where do I find the claim which we made, which we wanted to show in substeps 1 to c is, yeah, what we needed to show is this here, which is some things are there, this is there, this has the wrong factor still, and other terms are still a little bit annoying. The point C is to show that this vk minus yk is nothing else but square root of q times yk minus xk. And then you see that this goes in the right direction, right? We have y minus x, here we have v minus y, but if we subtract, we get rid of this 1 over square root, and the rest also comes together, and this this proves claim in 3. Okay. Yeah. So, okay. Yeah. Sorry for the mess, but this is just how it is. So we can now work with the following thing. We know that f of xk is smaller or equal the minimum value of phi k over all x, which we denoted by phi k star. So this is what we know now. Okay, not totally done, but we are close. So this was the sub-step, and now we are at step 4, already on page 10. And here we're going to use, or going to show that fxk minus f star which is now by this here smaller than phi k star minus f star. And now we use that this phi k star is the minimum over phi, so we can plug any x in here. So what we plug in here is x star. Okay. But for the phi k, we know from step 2 a recursion that we can estimate this from above. Oh, so this was claim 2 actually. Claim 2 was this, and we now use this in here. So we estimate, make it still larger, and we have to plug in x is equal x star over there. So this gives you an f of x star plus 1 minus 1 over square root of q to the k times phi 0 of x star minus f of x star, and here we have parenthesis is gone, and this is another f of x star, and you see that these guys here cancel, and you arrive at 1 minus 1 over square root of q to the k, and here we plug in phi 0, which is f of y 0 plus mu over 2 x star minus y 0 squared minus f star. And I think okay, by strong convexity again we can so strong convexity here in this case, noting that the gradient of f of x star is 0, we arrive at 1 minus 1 over square root of q to the k times, and then it's mu plus l over 2 times the norm of y 0 minus x star squared. And that's actually the first inequality which we'd wanted to show, right? We have this f of xk minus f star. Here we have the contraction factor and something which is determined by the initialization. So this 9. This shows that here, and this is just a very simple consequence. So to go from here to there, which would be step 5, probably right here. So step 5 would be to prove the second inequality, which is this. We just note that in general, also by strong convexity, y xk minus x star squared is smaller than 2 over mu f of xk minus f star. So we just can estimate here from below by mu over 2 times this, bring mu over 2 to the other side, do the calculations, and enter from here to there. So that's it. Okay, so if you think this proof is hard to follow, you will wholeheartedly agree. It's a mess, so I tried my best to make it simple, but probably one can do better. So if somebody of you kind of understood the inner workings of the proof and can compress it to just 2 pages or something, and can explain why it's like this would be awesome. But I don't have an idea how to make this any shorter, unfortunately. Okay, but now, okay, the proof is correct, so the result is correct, and that's what we need to know. So let's write down how good we are in terms of known upper bound and worst case lower bound. So what we get here is the theorem we just proved shows us this upper bound here, 1 minus 1 over square root of q to the k times square root of q plus 1 x0 minus x star. So that's our upper bound. And what is our worst case lower bound? The worst case lower bound looks slightly different. It looked like square root of q minus 1 over square root of q plus 1 to the 2k times x0 minus x star. So that's different. And how do we compare? So first, this has a larger exponent here. So of course these two numbers below the exponents, they are smaller than 1. So they go to 0 geometrically fast. That's good. So we have this factor here, but that's a constant factor. We should not kill. Probably that's not that bad. But now the question is, how much smaller is this guy than that guy? And so here's something how you can estimate that. So one thing. So what we need is this estimate is just 1 plus t is smaller than e to the t. And that is just Taylor expansion. Now this holds for it holds globally, I guess. Yeah, it holds globally. So this is the exponential function, and this is just the Taylor expansion at 0. So this is just 1 plus t. So it holds globally for all t. If we do that at t, and of course if it's like this, we could also raise it to the kth power. It still stays true. Probably only for t larger than -1, but that's fine. Yeah, I think we need t larger than -1 here. And if we now take t is 1 minus r, then we will get that t minus 1 over r to the k is smaller equal to e to the minus k over r. Okay, that's one consequence. And another thing is, so this is one thing which follows from here. And the other thing which we can set is we can also write that e to the minus t is smaller than 1 over 1 plus t. This also follows from here by dividing. And then set t is something strange, 2 over square root of q plus, minus 1. And then we will get that e to the minus 2 over square root of q minus 1 is smaller than 1 over 1 plus, you just put it here, 2 over square root of q minus 1. And actually this on the right hand side evaluates to square root of q minus 1 to square root of q plus 1. So so we have this here and that here, and this we could also, I could have even written this with r is equal to 1 over square root of r equal to square root of q. So why did I do that? I did that because this gives us that this upper bound 1 minus 1 over square root of q to the k without the factor is smaller than this guy here, e to the, well, let's write it like x minus k over square root of q. And for the lower bound, which was square root of q minus 1 over square root of q plus 1 to the 2k, we could bound that from below here by, so we have to raise this to the kth power, and we end up with exponential of minus 2, we raise this to the 2kth power 4k divided by square root of q minus 1. So what do we see? We see, of course, this is still smaller than that, because so this has to be smaller than that. So, and especially we have this factor of 4 over here. But this here we have, so it decays like e to the minus something times k, and this something here is much larger, smaller than that. So here we have 4 over square root of q minus 1, and here we have just 1 over k square root of q. 4 over square root of q minus 1. Yeah. So this decays faster, but this is not too far off. So it's just a constant factor, but we still have this dependency on square root here. So it's not that much more, but it's more. So I think these two things are a little bit simpler to compare than these two things, at least for me. Okay, so what's the question in the chat? So the accelerated gradient method is actually, I should have said that. So maybe do the numeration. And actually, so it seems like I ran through this proof pretty fast, but because, so in case you got lost in the proof, I think that's okay. It's just a lot of details. So there's no thread through the proof that I could have explained, so because I don't know any. We still have some time, and maybe we should just really talk about this momentum comment that you just made, but it's an excellent comment. So I thought I don't have time for motivation of these accelerated gradient methods here, but now I still have 50 minutes, so maybe I can do that. So momentum. Momentum is the behavior of something which is dynamical. So if you have a point of mass which moves by force, so let's say in gravity force or something, and then if a mass moves, it has momentum, which means it cannot stop immediately. If you want to stop it, you have to apply another force to stop it. So if something moves at constant speed, it keeps moving at constant speed as long as nothing is going to stop it. And so maybe I can open up the other motivation I did at another time and then show you how this works. Let me check. It will take a minute to bring that up here. Here we have that. Okay, so maybe I just show you the motivation. So why is this here related to momentum? I says even in the discrete setting it looks like momentum. So kind of our point so the iterate is now the point of mass in R2. So I is moved from here to there, and the gradient method would say so just stop here and take the turn wherever the gradient points you. So, but momentum says so I just came here and move a little longer in this direction, then take the turn for the gradient. So we just move a little longer in the direction where we came from, so we kind of keep our speed. Okay, one can make this connection a little bit more intuitive. So connection to momentum. So the standard gradient method, xk plus 1 is equal to xk minus h gradient of xk. You could reformulate this like this. So I just moved the xk over here and divided by h. And here's a minus sign, which is important. So, and if you now if you now let the step size h go to 0, then also this goes to this, and so this turns into, so roughly for h goes to 0, this turns into something like x dot, the time derivative, just with respect to an artificial time. And the right hand side goes to negative gradient dot x. So this is now, so this differential equation here turns into a differential equation. And so, or put differently, if we have this differential equation, which is a differential equation in Rn, and apply the forward Euler method to solve it, we will end up exactly with this. So this is the numerical scheme, a simple one, to solve this descent equation here. And so in continuous time, this has a nice interpretation. So what one can do is to, so for f, we write the contour line. So this should be the contour lines of f, which means f is large over here, smaller there, smaller, 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 and here is the minimum of f. So we also know that the negative gradient points in this directions, right? This is where the negative gradient points. So and here this, it always points downwards and is always perpendicular to the level lines. So and so this differential equation says if you start here, you always move into the direction of the negative gradient, and the speed is the size of the negative gradient. And so really what happens in practice, if you now solve this numerically with good accuracy, you will see that the trajectory will look like this, which is good. So theoretically, this is a very good differential equation which moves you directly towards the value of the minimum. But numerically, things look a little bit different. Numerically, what happens is that you have steps over here, and what you end up with slight oscillations in this direction, and these oscillations do not cancel out. So numerically, you get these oscillations into the wrong direction. So the minimum is this way, but numerically you always see the oscillations like that. So of course, if you start from here, you go directly to the minimum, or from here. But if you start from here, you have go to like this, and numerically you will not get rid of oscillations in these directions. Okay, so and then one idea is, so and the physical interpretation is, if you think of f as a bowl, so the gradient of f always at some point points in the direction where it really gets smaller faster. Then this describes how a massless point moves, so massless and frictionless point moves down the bowl. So if you put a very light piece of soap into a slippery bowl and let it slides on this trajectory. So no mass and no friction. But if you add mass to the differential equation, the mass introduces momentum. So this is for a massless point with no friction. This point with mass and still no friction, this will give you a differential equation which looks like this. So this is taking into account for the mass. So the larger the gamma, the larger the mass, so the more momentum does the point has. And what you then observe in practice, so numerically, is that so with some mass here, you will see that the point moves like this. And if you make it larger, it even may go completely wild. So, but in between, there is something which still goes nicely over here. So maybe that's a short overlap. So depending on the size of gamma, you get different trajectories, and so for gamma positive, you get overshooting, but okay, something like this. But what happens with the numerical scheme is that this mass, this extrapolation here, pushes you a little bit more into the direction of the throw here, a little bit more in this direction. In fact, so if you now try to solve this equation with a very simple numerical scheme, and the scheme can, for example, look like x double dot is then approximated by a second order difference, xk plus 1 minus 2 times xk plus xk minus 1 over, and then we need, I guess, h squared. And of course, x dot is usually approximated by a forward difference, xk plus 1 minus xk divided by h. And if you plug this both in here and do some math, to just do the calculation and solve for xk plus 1, you end up with xk plus 1 is equal to, and I think I have it here correctly, xk plus gamma over gamma plus h times xk minus 1 minus h squared over gamma plus h gradient f of xk. So this is what you get, and what you see is that this here, that's the extrapolation step. But you also see that you don't have the extrapolation here in f. You only have the extrapolation outside of the gradient. And methods like this are called heavy ball methods. They are even older than the accelerated gradient method, a few years. I think they're from the 60s by Poljak. And this accelerated gradient is from the, I think, 80s by Nesterov and Nemirovsky. So this is old, and I'm not sure how what you can show for the case of general convex functions. What Poljak observed is that if f is a squared function, a quadratic function, so like ax minus b squared, then this actually converges pretty nicely, and so it's almost comparable to conjugate gradients, and so this converges much faster than the standard gradient method. I think the analysis for general convex functions, I'm not sure what this current status is. Sorry, I don't know that. But this is used a lot. This momentum idea. It's used a lot, even for the training of neural network. I think it's part of ADAM, the most popular optimizer for neural networks. So it involves the momentum idea. Let's say that. But still, in the case where f, I think for the case where f is convex, it's known that the method converges. In case that f is not convex anymore, I'm not sure if anything is known. Probably it's known that it converges somehow locally, but I'm really not sure. At least I'm pretty sure that nobody could really prove that this momentum idea is provably better than not using momentum. In practice, it's always not a bad idea to try a little bit of momentum for gradient methods, but theory does not guarantee that it has to work. Good point, and we had the time to discuss this momentum thing here. Of course, you may think, well, if you went from first to second derivatives, why not all go on to third or fourth derivative? And actually, if I once read the Polyak paper, he does that already. Back, I guess, in the 60s. He tried to work with nth order differential equations here, but comes to the conclusion it doesn't get any better than that. So of course you then get a further recursion where you also keep in mind the number of previous iterations and take linear combinations of this. And it still is actually all still below under our umbrella of first order method because we move in the span of the previous iterates somehow. But he shows, if I remember correctly, that higher order differential equation doesn't pay off anymore. But going from first to second gives you something. Moving on to third or fourth doesn't give you anything more. Okay, so yeah, thanks a lot for keeping up with me here to this probably most technical lecture in the full course, not only for the course here, for the short course, but also for the long course. This has been probably the most technical. Yeah, the reason for the oscillation, I can tell you a little bit about that. Of course, the oscillation depends on step sizes. And actually, the step size makes a huge difference always for gradient method, but they are kind of impossible to choose in the best way. What I can show you is, and unfortunately I only can show you 2 dimensions. Because in 2 dimensions, there's always a step size which brings you to the optimum in 2 steps, no matter where you start. So if I start here, this is my x0, then this is the gradient direction, and so I should find my next iterate somewhere on the line. And actually there is a line, the point on here, where the next gradient points directly to the minimum. So for example, it looks like it's maybe over here. So if I would choose my step size that my x1 would be there, then I would go to the minimum immediately. But how should I know? How should I know that I should stop here to get to the minimum? So what one often does is taking the constant step size 1 over L, if one knows the Lipschitz constant of the gradient, and this brings you somewhere. What one can also do is to do steepest descent, saying I want to go as down as possible along the line. And if we do that, it's not the best thing. So it's a good thing, of course. For each step locally, it's the best thing you can do, but you will end up somewhere over here. And what you then see is, so actually that was wrong here. Sorry, that was wrong. Now here there's still the gradient. It depends. So this was probably not the point what I wanted to show. So and I would need to find a point such that the next gradient points directly toward the minimum. There is it, but it's not that one. My sketch here is a little off. So, but what happens if you? So this was here. Sorry, this is wrong. But what happens if you go down as much as you can along this line? You end up somewhere maybe here. But what is then true is that then the next gradient will be perpendicular to the previous one. So you'll move in this direction. And this will stay true. So the next gradient will move then somewhere here. The next gradient will again be perpendicular. So we always have perpendicular gradients. So that's one thing which is really true for the steepest descent gradient method. If you move down as much as you can, the next gradient will be perpendicular, and the next will again be perpendicular, and so on and so on and so on. So you see that at least if you do that, taking the steepest descent method, your trajectories will always look like this. And this will not go away. You will always have these perpendiculars, these right angles over here. And for different step sizes, it's a little bit different. It's hard to visualize or to guess what would be the step size 1 over L in this case here, but so the oscillations depend on that. Okay, so I think our time is up. Thanks for the questions, and thanks for keeping up. Next lecture will be the last, and we'll make a very nice generalization, which is actually simple. So this here only can minimize one smooth convex function, L smooth convex function. So, but sometimes you have objective where you have non-smooth terms in there, and then what we can still do is to make an adaptation of the method, which is the so-called proximal gradient method. So the prox can take care of the non-smoothness, the gradient take care also of the minimization, and if you combine them properly, you get a nice and also acceleratable method for non-smooth optimization. Okay, thanks for listening, and see you tomorrow.